What we're going to be looking at here is the 5 problems on page 35 of your chapter 17 notes. So these are a review of acid-base equilibrium and also KSP equilibrium. So we're going to begin with number 1, of course 1A, and it tells us to calculate the solubility of calcium oxalate. Never mind. We are going to calculate KSP using the solubility. So the question is KSP equals question mark, and we know the solubility is this value 6.1 times 10 to the negative third. Notice how that's grams per liter, okay? In order to figure out KSP, we're going to set up a Rice table, and we're going to plug in the solubility, which by definition, the solubility is how much dissolves. But in a Rice table, we need to use molarity, not grams. So the first task is going to be converting our 6.1 times 10 to the negative third grams of this compound into moles. So we're going to go from grams to moles. Now, it's grams per liter, so I'm going to put the liters on bottom so that when I solve this, I will have moles over liter, which is the same as molarity. So 1 mole, the compound is calcium oxalate. Adding all that up, the molar mass is 128.102. So we divide these two numbers, and we get that the molar solubility for this compound is 4.8 times 10 to the negative fifth. So again, this number is what I'm going to remember. That is the molar solubility of the compound calcium oxalate. So we're going to set up our Rice table showing calcium oxalate solid trying to dissolve as much as it can, calcium and oxalate. Good news here is it's just 1-to-1 ratio for calcium and oxalate, so nothing crazy is going on with coefficients. So to set up this Rice table, we do a lot, 0, 0, because it's no common ion, nothing's present before we start. The minus x right here, remember that this is the solubility. So instead of calling it minus x, we're going to plug in our molar solubility that we just solved for. This value right here is solubility. So it's minus 4.8 times 10 to the negative fifth. So this is going to be plus 4.8 times 10 to the negative fifth and plus 4.8 times 10 to the negative fifth. This value isn't going to matter because it's a solid. It's not going to go into the KSP expression. And these are both 4.8 times 10 to the negative fifth because, again, nothing weird is going on. So we're ready to solve this. KSP is just the calcium times the oxalate. Let me get the charges in there. So we just plug in the equilibrium values. For each of these, it's 4.8 times 10 to the negative fifth. So we would square it because it's just the same number each time. So our KSP value is 2.3 times 10 to the negative 9. So this is the answer to 1A on page 35. We're now going to look at 1B and see how it's different. The main thing here is that the compound Bi bismuth iodide, it has a subscript right there. So what this is going to do is when we're doing our changes line for the iodide, it's going to be plus 3x. That's one thing that's going to come into play. The other thing is that when we set up our KSP, the iodide value is going to be cubed. So if you have subscripts in a KSP type problem, it affects you twice, in the changes line and in the KSP expression. All right, on this one, they're nice. They gave us the solubility as moles over liters, so we don't have to convert from grams like we did in the previous one. So we can just start with our Rice table. So again, it's bismuth iodide. There's 3 iodides, solid, becoming the bismuth 3 ion and iodide, but there's 3 of them. They start at 0 because nothing weird is going on. This starts with a lot. Okay, again, this value right here, the changes, the amount that dissolves of the solid is the solubility. So we plug in that value, 1.32 times 10 to the negative fifth. And it gave it to us as molar, so we didn't have to do a conversion. This is plus 1.32 times 10 to the negative fifth. The iodide value is going to be plus 3 times that value, 1.32 times 10 to the negative fifth. Because again, the coefficient right there means that we need 3 times as much. So, those are the values there. This one doesn't matter. The KSP expression on this one is going to be bismuth times the iodide cubed. So we plug in our values, 1.32 times 10 to the negative fifth. The iodide value, it's 3 times 1.32 times 10 to the negative fifth, and it's also cubed. So make sure you don't forget to multiply this one by 3 before you cube that value. So type all that into your calculator, and what we get is 8.20 times 10 to the negative 19, and it's a K value, so we do not have any units. Okay, next we're going to move on to number 2, part A. So it's calculate the solubility of the compound in moles per liter, ignoring the acid-base properties. So we're solving for solubility, so this time it's the opposite of problem number 1. We're looking for that minus X value in the Rice table. Okay. So for the first one, again, we're going to start by setting up our rice, showing silver phosphate. So Ag3PO4, we know we're going to have to pay attention to that 3 because that's going to show up as a coefficient over here on the other side. No common ions. We are going to put a lot of that stuff, and what we're solving for here is what is X? What is the solubility? Because that's always the value right there, solubility. So this is going to be plus 3X, and this is going to be just plus 1X. This value won't matter, 3X, X. Okay, we're going to have to be very careful here because we have the KSP, which is known. It's going to be equal to the silver value cubed and the phosphate value. So when we plug in the values that we know, KSP is 1.8 times 10 to the negative 18 equals 3x cubed times x from the phosphate. So when you kind of work all of this stuff out, 3x cubed times x, the 3 cubed ends up with being 27. Of course, x gets cubed as well, but we're multiplying by the other x, so it ends up being x, ooh, that should be an x to the 4th, okay? So if you don't know how to do 4th root, you will raise to the 1/4 power, and that's how you solve for that. So feel free to pause for a second and solve this out, solve for your x value. When you do, you get X, which is the solubility, so this is the answer. You get 1.6 times 10 to the negative 5th, and it's molar, because that's the molar solubility. Let's take a look at part 2 and see how this one is different, or sorry, part B. So this is the mercury chloride compound. They do specify that the ion is Hg2 plus 2. That's actually the mercury 1 ion, and they're telling you that to clarify how the coefficients will work. So it's the same process. Hg2Cl2, double arrow. So they're telling us that the mercury is Hg2 plus 2. And so since it's Hg2, and that's what was in the formula, there's one of them. So I know it's weird, but the coefficient here is 1. But we do have 2 of the chlorides, so that's going to matter. Okay, a lot minus x isn't going to matter. They start at 0 because it's not a common ion problem. This is going to be plus 1x, and this is going to be plus 2x. So x and 2x. From here out, it's very similar to the previous problem. We just have different numbers. So KSP will be the mercury with no exponent, the chloride squared. So we plug in what we know. KSP is 1.1 times 10 to the negative 18. Equals x for the mercury 2x for the chloride, and make sure you square it. When you solve all of that x stuff out, we get 4x cubed. So again, to solve for x, you're going to need to first divide by 4 and then take the cube root. To do that, you can do the cube root in your calculator if you know how to do it, or raise to the 1/3 power. So feel free to pause, solve for x. You should get 6.5 times 10 to the -7 molar. All right, so these two problems are very basic KSP problems where we either are solving for the solubility from the KSP or going the other way, solving for KSP using the solubility. Problem 3 is also a KSP problem. We know that because it gives us a KSP value. And in this one we have zinc sulfide. We're trying to figure out how much will dissolve. That's another way of saying what's the solubility. If we have 300 milliliters of a 0.05 molar zinc nitrate solution. In problem 3, the question is what mass of zinc sulfide will dissolve in 300 milliliters of 0.05 molar zinc nitrate. If you notice, it's telling us that zinc sulfide is trying to dissolve, and we already have zinc nitrate. The zinc nitrate is a fully soluble salt because it's a nitrate. And so before the sulfide compound can even begin to try to dissolve, we already have 0.05 molar zinc. Okay, so this is our common ion, zinc, and it's going to be present already when the zinc sulfide begins to dissolve. So when we do our Rice table to solve for the solubility of zinc sulfide solid, the zinc over here, initial, is not going to be 0. The sulfide is 0. We don't have any of that. But this one's going to start at 0.05. So this is a lot. Minus x. This is, again, in the end, kind of what we're solving for. How much will dissolve? We'll just have to convert it to grams. This is going to be plus x, and this is going to be plus x. So x, 0.05 plus x. Doesn't matter. Focus on the zinc right here. This minus x, or sorry, this plus x will be negligible because it's from a non-zero. This x matters on the sulfide because it started at 0. Adding some on is significant, but adding on a very small amount to 0.05 is not going to be significant. So we plug into the K expression, which it's just a 1-to-1 ratio, so KSP equals the zinc times the sulfide. So 2.5 times 10 to the -22 equals 0.05 x. Pause for a moment, solve for x. And what we get is our x value is, I did not write it down. X is 5 times 10 to the -21. Now that's molarity, moles over liters, okay? So if we had a full liter, 5.0 times 10 to the -21 would dissolve. We don't have a full liter though. What we actually have is 300 milliliters or 0.3 liters. So that's 30% of a liter. So I think that we would just multiply that by 0.3 in order to convert this into how many moles will it be for every 0.3 liters. So if we multiply by 0.3, we get 1.5 times 10 to the -21 moles. Finally, what we need to do is convert this value, this number of moles, into grams because that's what it asks for. So we're going to take our 1.5 times 10 to the -21 moles. Of course, to convert from moles to grams, looks like we're going to multiply by the molar mass. So feel free to pause, calculate your molar mass of zinc sulfide, and finish this out. What you should have calculated for the molar mass was about 97.38. So when we multiply this by 97.38, we get 1.46 times 10 to the -19 grams. All right, let's move on. All right, let's look at problem number 4. We're moving from KSP into acid-base equilibrium, and this is a great practice problem with a titration. it says that we have acetylsalicylic acid. We have 2.51 grams of this, and we titrate it, and it requires 27.36 milliliters of 0.5106 molar NaOH for the complete reaction. The complete reaction indicates that that is required to get to the equivalence point where the moles of acid equals the moles of base. Moving on, it says the addition of 13.68 milliliters of HCl to the flask with the aspirin and the NaOH produced a mixture with a pH of 3.48. So that sentence is kind of tricky. We'll come back to it. We're going to use this information to find the molar mass and the Ka value, assume any assumptions that you make. Okay, so let's begin by focusing on the beginning of the problem. To neutralize the 2.51 grams of the acid, which I'm just going to abbreviate as HA, it requires 27.36 milliliters of 0.5106 molar NaOH. Okay, it says this is required for the complete reaction. So what we know is that at this point the moles of HA equals the moles of NaOH. So if we want to solve for the molar mass, which is our first goal, molar mass is grams per mole. So if we want the molar mass of the HA, we just want to plug in the number of grams of HA, which was 2.51, divided by however many moles that is. Now, we don't just know how many moles that is, but what we do know is that the moles of the acid equals the moles of the NaOH. So we're going to solve for the moles of the NaOH, and that number is going to go down here because it's also equal to the moles of the acid. So this is pretty straightforward. 0.5106 molar for the NaOH equals the number of moles over the number of milliliters, which is liters, 0.02736 liters. So take a moment, pause, solve for your moles up here. And what we get for our number of moles is 0.014. So we're going to plug that in down here, 0.014. Because again, the moles of the NaOH equals the moles of the acid. That's what we're plugging in down here. So we just divide these two, and we get the molar mass to be 179.3 grams per mole. So if you know the equivalence point and you know the original mass of the acid, it's pretty easy to get the molar mass. Okay, let's take a look at the second part. The second part says that after we had already neutralized it, we're going to do what's called a back titration by adding acid. So we already had NaOH neutralize it. We're going to back titrate it with hydrochloric acid to take it back to the acidic side of the equivalence point. So notice that we add 13.68 milliliters, and it was 0.5106 molar. I'm going to skip the work, but if you do something similar to what we did before, figure out how many moles of HCl that is, what we get is 0.007. Now here's where you just kind of have to know what to look for in a titration problem. You always want to look for what's called the half neutralization point. If you think about it, it required earlier 0.014 moles of NaOH to get us to the equivalence point. We're taking it back by half that amount. So I know this is kind of a weird situation because we're back titrating, but what we have here is the half neutralization point. And what we know at the half neutralization point is the pH equals the pKa of that weak acid. Okay, so they tell us the pH at that point was 3.48, so the pH equals the pKa. So to solve for the Ka, it's going to be 10 to the negative pKa, so 10 to the negative 3.48. So when you plug that in, what we get is 3.31 times 10 to the negative 4. And it's a Ka value, so there are no units. Our final problem, finishing up, number 5, is a buffer problem. It doesn't say the word buffer, though, so you have to know why it's a buffer. We want to calculate the mass of sodium acetate that needs to be added to 500 milliliters of 0.2 molar acetic acid to create a pH 5 buffer solution. I lied, it does say the word buffer, but the reason it is a buffer is because we have sodium acetate and acetic acid, because we have a weak acid with its conjugate base, the acetate, the sodium, doesn't matter. Weak acid with its conjugate base means that this is a buffer. We know the pH, and so we're going to use the HH equation, the Henderson-Hasselbalch equation, to solve this. So if we remember, the pH equals the pKa plus the log of, and then this ratio over here is the conjugate base over the original acid. It's always the conjugate over the original. So we're going to plug in what we know. With the pH of the solution is 5. The pKa is the negative log of the Ka value for this acid, which is 1.8 times 10 to the negative fifth. That would be given on the AP exam. Plus the log of the ratio of, again, the base, the conjugate base over the acid. Okay? All right. The first thing I'm going to do is I'm going to rearrange this, and I'm just going to solve out for this ratio. Okay, so feel free to pause it for a minute, solve for that ratio. What we get for that ratio is 1.8. So 1.8 equals the concentration of the base over the concentration of the acid. Now, one of those was given in the problem. The acetic acid molarity is 0.200. So we're going to plug that in. So 1.8 equals the concentration of the base. Again, the base is the conjugate base, the sodium acetate, over the 0.200 molar acetic acid. Okay, so you solve that out pretty easy. We get that the concentration of the base is 0.36 molar, and again, that is the sodium acetate. Well, we know that molarity is moles over liters, and it's important to note and remember in this problem that we don't have a full liter. We have half of a liter, 500 milliliters. So this is 0.500. So we're getting really close. Pause, solve for your moles. What we get for moles is 0.18 moles of sodium acetate. If we convert from moles to grams, the molar mass is 82.046, and we are done. When you multiply this out, you get 14.8 grams. So this is a great practice problem because of what we had to do earlier and solve for that ratio of the base to the acid and get that value of 1.8.